once again, you can ask question in any language that I can understand. Em particular, as pessoas os brasileiros podem perguntar em português, não tem nenhum problema. So let's start. Okay, so the basic idea that I want to follow. Maybe just a moment. Okay, so we just want to get a basic definition of these guys, the homologies, and cohomologies and homologies. And then from the next lecture, actually, we want to go to study the topology of algebraic varieties. So the idea is that if somebody has never done a course in algebraic topology, I hope that in our way to study the topology of algebraic varieties, he will get familiar with this topic also. Okay. So what we did, last time. So it is. Let me see. So so we start from topological space, and at the end we define the CS0 covering sheaf S, and then C1 delta S covering sheaf S. We define this complex. Let me see. That is P S S delta delta, and very fast I will say that at the end this proposition I mentioned but didn't prove, that the composition of two consecutive delta is 0, and that's for this reason the image of one delta. If, for example, if we fix, let's say here, is in the kernel of the next delta, and that's we defined the cohomologies. This I will, for simplicity, I will write kernel delta image delta. So this is let's say another delta closed cochains, and this is the consist of delta exact cochains, and well, the definition a priori depends on the covering that we have taken, this calligraphic view, and we have to make it kind of independent of this covering. This process of making independent of covering, we will discuss it today. But at the end of the day, what is for computation, we will always use covering. Yeah. Something that we will talk today is which kind of covering we can take such that and we can work with this covering and then forget that our cohomology depend on this covering. Anyway, okay, so the basic idea is that we want to make it this independent of the covering. So let me so I am now talking about section 2.3 of my book with my former student Villaflor. Okay, so this process of making independent of covering is a kind of classical procedure, and we will never use this procedure in the course. This is just for the sake of completeness. that the idea is complete in the sense that I want to write this notation. I want to make this equal to this one, but at the end there is u, and apparently my notation depends on u. Okay, so before going to do this one, let's just a little bit review this delta composition with delta equal to 0. This is a kind of classical statement. Okay. Okay. So just a moment. Let's just present again the window. Okay. Okay, so the proof of this delta equal to a delta is just kind of natural. I mean, you just take a delta. You have to take a delta square f, and delta square f is p plus 2 complex. So it has it is p plus 1 complex. It is its elements are defined on the intersection of f is p cochain. So delta to f is p plus 2 cochain. So its elements are defined in p plus 2 one intersection of open sets. That's why we have to evaluate our here. And then we just write the definition. In the first, we first write the definition of one of these deltas. We will get this expression. And once we write the now we write the definition of this delta again here. And the point is that in delta f, its indices, one ij is lacking. This hat was just neglecting ij. So we have to distinguish between the other index that we are going to write. Here, let's say we want to write again definition of delta, but we have to take the one which is less than j minus 1, the other one bigger than j minus j, because the minus signs that we are taking, it will be different because of this missing ij. And when for the second delta, when we write this definition, we will see that there will be two terms with iji and the ika missing. And in these two terms, the corresponding signs will be different, and so they will cancel each other, and then we will get at the end the 0. So I think this is a kind of to say classical computation in algebraic topology. In many other situations also this pops up, like singular homology. So let's just not focus on this one. Maybe ask any question. Okay, so if there is no question, so we have already this delta. Then we define our cohomologies. So let's I was planning not to present this this process of making independent covering, but because of some homotopy argument that appeared in this, I will present this one. Okay, so the idea is that we have to cover, we have to take, okay. So the idea is that we want to take all covered and take a kind of limits. And this will produce very ugly definition, but at the end of this today's lecture, we will see that we can forget this ugly definition. So we have to define a kind of order between coverings, and we say that U1 is a refinement of U2 if there is a map from phi I1, I2 such that U I1 is inside U1 I is inside U2 phi I. So the idea is very simple. So I have, let's say, this small open set U1 I, from which one this the first covering. This is the covering one. So the idea is that each open set of the calligraphic U covering, it must be inside an open set of the second covering. And then there is a map. So there is the open sets are indexed by I. So this we have to map let's say this phi I. And yeah, let me see. Okay. Okay. Anyway, and so after defining this one, well, the argument will be that this set of all open covering, let's say the set of all open coverings of X together with the refinement relation is a directed set. What it means, directed set, if I take U1, U2 to any two covering, which might have nothing to do with each other, at the end I can take U3, which is a refinement of both U1 and U3. And the idea is also a kind of simple. Maybe just okay. The idea is simple. If I have let's say the two covering, let's say this comes from the first covering, this comes from the let's say this I, and then let's say this, and then at the end of both calligraphic U1 and calligraphic U2, they cover the whole space. At any point I take, it will be in some any point of the space X will be on some U1I, it will be on some U2J, and then I will take a small open set which is both in U1, U1I, and the U2J, and then I will construct this U3 covering starting from this. So then this will be the U3, and the U3, let's say K, and so the map, the refinement map will send K to I and K to J. So this is a kind of a nice exercise in basic topology. So let's see what we want to do. So maybe this one I have to explain in the paper. So something very important that also every refinement of covering will induce a co-chain map. So let me explain in this the paper what it means, co-chain map. So, but I say okay. So let's just stop sharing. Okay. So maybe back to my handwritten written paper. So I have U1. It's a refinement of U2. Oh, let's say that's right. Calligraphic. So at the end, it means that from the index set of one to another one, I have this map from the index set such that let's say U1I is inside U2 phi I. And from another side, I define this one, C0 US, maybe just write, let's say, the middle letter P minus 1, P, let's say U1. So I have the complex associated to the first covering, U1. Oh, I'm making mess. U1, U1, S, and so going on. And I have the same thing from for U2, CP, U2, S, sheaf S, CP, U2S, and so on. So first of all, we have to, well, again, both are all delta. I will denote the same delta. And so when U1 is the refinement of U2, so we first observe that there are canonical maps from top to down. And what are these canonical maps? And in the text, I have put it as a phi. Again, we don't write different names for all these phi. So this means let's say the phi, or what is written in the text is phi S. So S, let's say, let me define this this phi. So S will be here. And I want to define phi S here. So phi S, so it must be evaluated on the intersection of I1, IP. So it must be element here. And oh, sorry, I have written the directions. The directions are wrong. Oh, sorry. So there is this. Let me make it. It's easier to make it. So this was 2. This is 2, and I have to go from the small, the bigger one to the smaller one. So it is down to up. So I have to take. So this means that I have to take. Maybe let's use some other. So I have to take S here. And so I have to define this phi S, which must be here. So I will take P plus 1 open sets, phi S. There will be some value of the phi S over the intersection of P plus 1 set. So what is this? This is just, let me, okay, so maybe I have used this in the text is different. Maybe this I will use this for a small phi, because my handwritten both big phi and the small phi is the same. Maybe this one. Let's say this one. Okay. So I have to define this one. So what I can do? So I can have the intersection. So this I0, I1, IP, they are in the indices of the smaller covering. So I have this phi I0, this open set phi I1, phi IP. These are indices of the bigger covering, and then this means that I can at the end evaluate S over this intersection of this P plus 1 covering, and then I can restrict it again to UI0, UI1 until UIP. this was just the intersection of maybe I might, if I want to make a picture for this is for p equal to, let's say, 1. So I have let's say this I0 and then I1, and then well, I don't write the corresponding U. Then this is becomes be a U phi I, maybe phi I1, and then phi I0, and I have taken S here. This means that I have taken S, which can be evaluated in this intersection, and at the end I am restricting over the intersection of these two guys. Okay, so and well, this is defined in a canonical way, and there is the word this defines a cochain map. So when you have this two complexes and the map between these two complexes, it is called a cochain map. If anything that you see which possibly commutes, it must commute. For example, here. So that means that this means that if we make maybe I make here. If we make from here to here this map, and then from here going to up, and then here it must commute. So so this means that at the end, delta, we simply write delta equal phi is equal to phi delta. This is just a kind of abbreviation that in each box, it doesn't matter how you go from here to here. Either you go with delta or phi, and then or you go first with phi and then with delta. Anyway, these are some details that I think it would be good to sit down and convince oneself that they are true. And one reason that I wanted to make this, wanted to present this this part, is the concept of the homotopy. For the people who has never seen this concept before, and they want to learn a little bit algebraic topology in the same time of the course. So let me again present window. Okay. Felipe, quando as coisas não funcionarem, você me avisa.
Tá certo.
Bom, okay. So, as I said, one reason that we are doing this process of making independent of covering, even so that we will never use it, is the concept of the homotopy that appear in this proposition. So the induced map. So the point is that we will have the induced map. It is also kind of immediate. Once you have a delta phi equal to phi delta, then you will have this map, which is well defined. Of course, one has to check that this phi is well defined. It means that here HP is some quotient, and maybe that just I do this a little bit. I will define it, not to be very fast, just to let it stop. This induce, which again I will define with the same phi, some map from HP P U1S U2S to H P U1S. So the idea is that at the end you take any class, and then you will associate the previous phi alpha, the phi that you have defined there. But these are classes, so one has to show that it is well defined. For example, if we take something exact, delta beta, so we have to prove that it goes to 0. And so let's if we take phi delta beta, and of course we have seen that phi delta is commute, so this is delta phi beta, of course phi with different domain, but at the end since also we have bracket, the equivalence class, so delta under this bracket it will be killed, and this is 0. So this is a kind of any cohomology theory at the end you have to we have this kind of argument. Okay, let's just go to the the page. Okay. Okay. See, so if somebody, well, one of the really great, let's say, revolutions in algebraic topology, has been this passage from purely topological arguments to algebraic argument. And something that I really enjoyed when I first learned this concept of homotopy. And of course, if you do a course in basic topology, you will see what is homotopy and so on. But now you will see that the concept of the homotopy has turned into something purely algebraic in the middle of the proof of this proposition 2-3. So we want to prove that this induced maps are independent of the refinement. This means that it doesn't matter how I choose this I1, the map from I1 to I2. If I have a covering, let's say U1, U2, and at the end of the day, I know that any open set of U1 is inside some open set of U2, I can choose. There might be many open sets of U2 that I can choose. So this means that I can choose this phi in many different ways. And so the proposition tells that this is independent of this phi, and the proof is a kind of good exercise to understand this algebraic homotopy theory. And I found it interesting to mention it during the course. Okay, so here it is not written in a very more pictorial way. So let's say we have to choose two different refinements, and so this will also induce a map of complexes, and we have to show that they are homotopic. It is homotopic to phi. But now I am going to a little bit explain what it means to be homotopic. Let me. Okay. So anyway, the idea is that I want to choose different refinement, and I want to show they induce the same element, same map in cohomology. And okay, so next I am going to explain what it means psi is homotopic to phi. Okay, so let's just again stop sharing. Let me see. Actually, I can maybe I do it. I do it. Let me see. I have different colors. Okay, let's go. So the idea is that in any case, I have the complex U1 attached to U1. I have the complex attached to U2. I have the map phi, And now I have the map also psi, which comes from the other refinement. From down to top, I have two maps. So the idea, the basic idea is that if I construct if I am able to construct a map from p plus 1 to p, let's say p plus, oh, sorry, there is mistake here. There is a c plus 1 here, c plus 1 here. So the idea is that if I am able to construct maps from here to here, so in everywhere, and let's call them H standing for homotopy. If I construct these maps, and these maps with the property that I need is this one: phi minus psi must be equal to delta, maybe let's delta H plus H delta. So let's a little bit analyze this one in the picture. So first of all, since these are abelian group, I have the map phi minus psi from down to top. Okay. Again, there is this. So from here, let me. I have to arrange for the black one. So from another side, also I have the map. Let's say going to here. Let's say delta from here. Maybe just write later. Going to here, and then by phi going up, and then no, there's the one delta H. Oh, sorry. From let me see. Oh, sorry. No, sorry. I made a mistake. First, delta H and H delta. So let's analyze. For delta, and then I have to make H. Let's say I have made just a moment. I have made a mistake or not? H. Let's say H delta. Oh, sorry. Actually, here. Okay. Well, let's say this. So from here we go with delta to here, and then I made let me say I have made H. Oh, I have made this p plus 1 U2. Oh, I have made it. Maybe I have made this. Actually, I have made this wrong. This is top to bottom. So let's again make the picture, because it will be. So let's do again. CPU1, CP plus 1. I will not write S U2. CP minus 1. So it was from U1. Okay. Now this CP U2 C plus 1 U2 C minus 1 U2. So then here there will be these two maps that I had. Oh, again, I'm making the wrong direction. And the one that I made it wrong. Actually, it was C plus 1. So it was these maps. C plus 1 U2. These are the maps H that I needed. So I need a map, let's say from C plus 1 U2 to CPU1, such that at the end phi minus psi, I want that delta H plus H delta. And let's a little bit analyze this. So I starting from well, if I take delta here, I make a go to if I take x here, I take delta x here, and from here I can go to those h delta x. From another side, I can go first by h. I will get hx, and then from here I take the delta, and then I will have a delta hx. So at the end of the day, these compositions will be from CPU2 to CPU1, and so both phi minus psi and both these maps, they have they go from CPU2 to CPU1. So one nice I think process in mathematics has been that the concept of the homotopy has turned to be the existence of this H. And the reason is that, and why we need this one, it is easy to see that if this happens, then phi and psi induces the same map in cohomology. So this means the same map HP, I will not U2 to HPU1. And this is a kind of again nice exercise. You have to let's say, let's for example do this. For example, phi x, let's say minus psi x. I take let's say x in, let's say this x in HPU2. So I have to show that they are in the cohomology are the same, but I use the equality. It is delta hx plus h delta x. But this is first of all, this is delta x is equal to 0 because I'm considering the this is by definition, because the bracket x is in the cohomology. The cohomology consists of just closed form, closed cochains, and this is also because of the quotient. This is 0. This is really 0, but this is 0 in cohomology, and at the end we will get something in cohomology. So I wanted to tell this one because this argument, this substitution of classical homotopy in topology with something purely algebraic, I think it's a very nice discovery in mathematics. So okay, so we understand that this map does not depend on the refinement. So let's go back to the text again. Present no window. And so in our case, we have to define let's say this homotopy map, and well, it is a kind of canonical definition, and so the homotopy map is attached to this two covering. It is a kind of sum that for the sum over this section. So we have to evaluate HS over I0 IP. And if I have taken two different covering, I have to, in some sense, use these two different refinement. I have to use these two different refinement in my definition of H. It turns out that we make a kind of sum L is equal to 0 to P with some sign, and until IL I use the first refinement, and from IL to IP I use the other refinement, and at the end I restricted over the intersection of UI0 until UIP. And again, I think this kind of definition, it's a matter of trying and failing, and I think the people when they started to invent this kind of things, they tried a lot, maybe changing the sign, making some combinatorics here, and at the end they realized that this kind of definition, it works perfectly. And yeah, and again, maybe you can justify this definition based on exactly the equality that you want. At the end of the idea that I want some definition of H so to satisfy this one. And trying and trying, then you will land on this kind of definition. So if you do a course in algebraic topology, of course, you will see a lot of this kind of homotopy between maps in algebraic topology. And this is a kind of one example in our course. Okay. Okay, so let's a little bit reach to this useless definition. And well, I say it is a kind of useless because really we'll never use it. At the end, we will use just a covering for dealing with cohomologies. So the P-check cohomology of X is a kind of this direct limit. Again, let's just we have to say that what is this direct limit of all covering? And so we just take a disjoint, kind of disjoint union of all these cohomologies for all coverings. And this is the reason why it's a kind of useless, because we are dealing with all coverings of a manifold or topological space that in practice you will never consider this all covering. And then we have to make it quotient to make it smaller. And when we take these two elements, alpha in HP, beta in HP, alpha relative to covering U1, U2, beta relative to covering U2, and we have to say that they are equivalent if there is a refinement U3 such that alpha and beta are mapped to the same element in this smaller refinement. And then one has to argue that at the end this is still an abelian group, and the only advantage of making this definition that we can replace here, instead of just U, we can write down X itself, because we have now it is independent of the covering. Anyway, well, maybe the one reason that really I a little bit talked about this part is exactly because of this homotopy argument. And okay, so maybe something else. Let me see what is the plan of today. Acyclic, exactly, acyclic covering. So as I said, we will never use this definition. At the end, we want to describe covering of a topological space, and at the end, just work with this covering, and at the end, just the combinatorics of the intersection of open sets of this covering is will govern the topology of X. Okay, no, actually not this. I will skip this one. During the course, we will be back to the sheaf theory, but for the moment, I am just doing the most basic one, such that to be able to talk about. Let me see. No, okay, that's just a moment. What I wanted to. Okay. So, and this is how, well, the section 2.6, how to compute check cohomologies. And this is important for us. Okay, so we need certain covering, and these are called acyclic with respect to the sheaf. As I said in my second lecture, for the moment, we don't need the general language of the sheaf. Just consider the sheaf, constant sheaf integers, or if you want real numbers or complex numbers. So this means that if for any open set, you just associate the ring Z or R. So maybe just okay, so the covering is acyclic if all the intersections, the cohomology are 0. And so this means that at least we must compute these cohomologies for certain open sets. Okay, so this is just a definition. So let's return back to our main examples, which is this constant sheaf Z and R. Let's say okay. So there is I will use this statement for a manifold X of dimension F. We have a covering such that all the non-empty intersections are diffeomorphic to Rn. And well, this is a kind of statement. Now I will tell where we will go to the reference. Actually, we will need that all these intersections are contractible to points. We call also this good cover, and it turns out that this good cover, a good cover is acyclic for constant sheaves. And okay, so this is kind of again classical statement, but maybe this is well, it is proved in Bott-Tu books. Maybe I stop sharing this one. Let's a little bit go to Bott-Tu book and just talk about your window. Okay, so if you go to Bott-Tu books, page 42. So the statement is there: a manifold in dimension, a point cover is called a good cover if all the intersections are different to Rn, blah blah blah. And then theorem 5.1: every manifold has a good cover, and if the manifold is compact, the good cover can be taken finite. This is also very important for us because just by combinatorics of finite number of open sets, we can compute cohomologies. And if you start a little bit reading the proof, you will see that the one essential thing is that it puts a Riemannian structure, Riemannian metric on this. And this is one of the few instances in our course that the metric will pop up. Almost 95% of the course there will be no metric. But this is one place that we will see a metric. And so the idea is that any manifold will have a metric, and then and another thing. So that this when once you have a metric, you can talk about geodesically convex balls in this manifold, and it turns out that the intersections of geodesically convex open sets in M, they are still geodesically convex, and then it uses the results of Spivak, where it is a Spivak that at the end the geodesically convex this open set, they are always diffeomorphic to Rn. So it is a kind of going beyond the content of our course. So, but if if somebody who is following the course, just a little bit reading and trying to get familiar with this proof, and you see that it's a kind of isolated statement in the middle of Bott-Tu's book. So actually, one has to go to Spivak's book to understand in a complete way this proof. Okay. So let's return back again to my own book window. Okay. And okay, so why we need why we need this cover? Because as I said, we want to work with cohomology relative to covering, and the definition by directed limit of all covering is kind of useless. So this is I will announce just Leray-Thom's lemma. If U is an acyclic covering of variety X with respect to a sheaf S, in our case, take as this ring of integers, and then you take a good cover. At the end, it says that this is this direct limit that we define here has limits, and actually its limit is just this HK over HKUS. So this means that really we don't need to work about work with this ugly definition of HKX. Otherwise, we just take a covering U, and all the computations we do with this covering. And for the moment, I will not do the proof of Leray-Thom's lemma. It is in the book. And but maybe after studying the topology of algebraic variety, once we want to do algebraic de Rham cohomology, maybe we will back to this and a little bit see how the proof works. For the moment, the moral of the story is that I need maybe I write it. Okay. So back to my camera. So the moral of the story is that I wanted to work with this Hn x and x. Then I have to just take U good cover. And once I take this good cover by Leray-Thom's lemma, this is just H and this U Z. And then you can also replace the Z with R and the complex number. Doesn't matter. Okay. So let me. Okay. So maybe enough. Well, I want to finish the check cohomology today, and from the next lecture I want to invest on topology of algebraic varieties. Maybe I have to say also this one. So something also that we need for our main theorem of topology of algebraic varieties, Lefschetz theorem, and then Lefschetz vanishing cycles, and so on. We need actually relative cohomology. So y a subset of X. Okay, and maybe very fast. I will do also this one, and for this I had to write. Okay, let's see. Okay. Maybe very, very fast I do this one. Today maybe I will talk more 10 minutes, but this is because next talk I want to go to my own book and the Lefschetz theorems. So we have okay. So we have this subspace H1 Sx. Just maybe imagine maybe as a submanifold, but necessary submanifold. And so I will define let's say this new sheaf. So maybe what I'm going to tell now, it is section 2.7. Let's write section 2.7 of my book with Villa Flor. My notes actually. Okay, so let's try to define this cohomologies X, Y, and then with coefficient in Z. Let's do this. So I will define this S tilde sheaf. Basically, it's a kind of constant. I mean, I want to say that the looking, let's say this Z as constant functions are open set. Just I want that sheaf of a function which restricted to Y, they are equal to 0. So what this will be what then? Then this will be Z if U intersected with Y is empty, and it will be 0 if U intersected with them Y is not empty. And just a moment. Okay, and this for this one, let's say let's connect it. And okay, basically I will use this sheaf in order to deal with this relative. It will be HPX is with this with S tilde, and okay, something else also that maybe let me say in this way. We will also introduce a singular homology and a cohomology. So, but in the sheaf theoretical context, this is going to be like this. I think maybe in order to proceed in the course, and if you have never seen a Czech cohomology, it would be really nice to do computation, at least to do one computation. Maybe one computation that I will suggest you to do. This is actually going to be the first exercise. Let's take a ball Bn inside Rn. This is just X in Rn, such that let's say x1 2 plus xn2 less than 1. And okay, then its boundary, let's call it, it's the sphere. Okay, I mean, in order to proceed with the content of the course, I think it would be nice to do this computation that at the end h n the n with the boundaries Sn minus 1 z, it is z. Just a moment. Z for let's go to m equal to n, 0 less 0 if it is m not equal to n. And my so just a moment. Okay, and I think the idea, I will put this one as exercise, and partially part of this exercise done in Bott-Tu's book, page 100. Maybe let's go to this this Bott-Tu's book and finish the course here. Let's. Okay, so let's read it. So if we go to let's go. Okay, so I think partially in Bott-Tu's book we have this exercise. He start to compute the check cohomologies of a circle and a sphere. And you see that he puts a covering of the circle with 3 open sets, so 3 open sets intersecting in this way. And for the sphere, he takes covering again with, let me see, again, 3 open sets, and their intersection is like this. And I think it would be nice that you do these exercises before we proceed further. And even so that I told that our main focus is the topology algebraic varieties. In the middle of our study of topology algebraic varieties, we will need the topology, the cohomologies of a sphere, and these spheres will appear as Lefschetz vanishing cycles. That's why this will appear in our purely algebraic context. And okay, maybe I was a little bit fast with this relative cohomology, but once again I want to tell that next lecture I will put my the main theorem that I want to prove in for algebraic varieties, and each time when I am using one some property of a cohomology or homologies, then I will mention it explicitly. So the idea is that in our way to understand the topology of algebraic varieties, we want to start getting familiar with cohomology theories. And I think this is possible, but okay, anyway, let's see if it works or not. Okay, I will stop here. Any question? Okay.
What would be the idea to show that check homology and singular homology coincide? I mean, besides, well, we need to show like the axioms, but what would be the idea for showing like excision and other things for check homology?
Okay, so maybe okay. Well, actually, this is a good question. We will need it. So, in I will see singular homology also at some point in our course. I want to start the course different. we will see check homology with Z coefficients, and at some point we will argue that they are the same. There is no difference. I mean, they are isomorphic. So one way that they are isomorphic, it's a kind of theoretical, saying that they satisfy the same axioms, and there is a very nice development in algebraic topology around 1950s. Eilenberg, Stinrad. And what they did is saying that, okay, at the end, if you have a kind of homology theory, let's say this Z, which satisfy a bunch of properties. If you have two of these guys and they satisfy, then they must be isomorphic. So a kind of cohomology theory is unique. Again, in the course, I will talk more about this one. But sometimes we will need explicit isomorphism. And the explicit isomorphism, actually, I will construct in the case of, let's say, algebraic de Rham cohomology and singular and this cohomology when multiplied with C. The answer would be that let's first construct one of these explicit isomorphism and then think about your question. For the moment, what I am saying, algebraic de Rham cohomology and this cohomology, after tensoring with complex number, we will construct explicitly the isomorphism. And the relation, the explicit isomorphism between this constructed from check homology and this constructed from singular homology and simplexes, let's do in our way when we are presenting the course. But these are a very nice questions because at the end, this just theoretical argument for us, they are not enough. We sometimes need to write down everything explicitly. Okay, so so I will finish the course here. So okay, maybe let me just stop recording and then.